All right, so welcome to Math 150 Multivariable Calculus. This is, I think, lecture 28. It's April 25th. I'm more confident about the second number than the first. And so what I want to do today is talk about Taylor series. We've already split it alphabetical order. We've already done some talking about Taylor series in one dimension. What I want to do today is generalize to several dimensions. A lot of times, books really only go up to second order Taylor series in several dimensions because for the most part, that's what you really need for the applications. I'll go through a little bit more generally as to how you do all of this. If there's time, I will give applications to finding max and minima that might have to wait till a later class. I will redo, I think I gave it the last time, the trick. Let's take this off now because class has started. I will redo the trick for finding new Taylor series expansions from old ones. So again, if you have to describe mathematicians with just one word, awe-inspiring, Huffington, that's a great word to use. Inspirational, great word to use. But amongst ourselves, we would probably use the word lazy. Whenever possible, we always want to reduce things to something that's already been done. And so we'll talk a lot about how can we do that with Taylor series. And so I can give you painful formulas to calculate things, but you can basically say, screw that. Let me just look at this the right way and reduce it to something I've already done. Right. So in one dimension, we saw that the Taylor series of f at the point x would be the sum and goes from 0 to infinity of the nth derivative at the point 0 over n factorial x to the n. More generally, we could have the sum and goes from 0 to infinity of the nth derivative at a over n factorial x minus a to the n. And you can talk about, does the sum converge? And if the sum converges, does it converge to the original function? Unfortunately, it is not enough to know that the sum converges to know that it converges to the original function. We saw the horrible function e to the negative 1 over x squared, where all the Taylor coefficients are 0, but the function is not 0. And this just tells you why pure mathematicians have jobs. Because things like this can happen, and this is why we spend so much time proving all of these different tests for convergence. How can I tell if a series converges? Why do I care? Well, I care because I might want to look at this Taylor series and I might want to know, is this going to converge to the function I'm studying? All right, so it comes down to, can we calculate these derivatives? And then put them together, and then does the sum converge? All right. One of the things that's nice is, if I look at the nth derivative of my Taylor series at 0, it is the same as the nth derivative of my function. And this is why we have the n factorial downstairs, because if I take little n derivatives, the x to the n goes to n, x to the n minus 1, then n times n minus 1, x to the n minus 2. So when I take n derivatives, x to the n goes to n factorial times 1. All the terms of degree less than n, if I take n derivatives, they go by pi. All the terms of degree n plus 1 are higher when I take n derivatives, they still have an x. So when I evaluate at 0, they're just 0. So the nth derivative of the Taylor series at 0 is just the nth derivative of the original function at 0. So the way you can think about these Taylor polynomials is I am cooking them up so that the first, if I take a Taylor series of degree 5, all the derivatives up to degree 5 agree with the derivatives of the original function up to degree 5. If I take it of degree 8, all the derivatives up to degree 8 at 0 agree with the original function at 0. And the hope is that, well, if all the derivatives agree, then the function should be close, at least for a small period of time. If I want to try to estimate where am I if I am driving from Boston to DC, if I know my instantaneous location, speed, and acceleration, do you think I can predict pretty well where I will be in 1/10 of a second? Yes, unless there's a stopped car right in front of me that I'm about to hit, I should be pretty confident about where I will be in 1/10 of a second. What about 100th of a second? Yeah, I'm confident in 1/10 of a second, I'm confident in 100th of a second. What about in 1 minute? No, 1 minute away, that's far enough that there could be, some slowdowns could be happening, could have some construction in the lane closure, could have people merging. 1 hour away, definitely not. So over a small period of time, if a lot of your Taylor polynomial degrees, say 5, agrees with the first derivatives up to 5 for the original function, you would expect it to be a good fit. And then what you would do is you would improve results. How good of a fit is it? How close is it? How far away can we go and still be within a certain amount of error? If I want to be within, 5 feet, how much time can I allow to elapse and still have my prediction within 5 feet of where I should be? Okay, so this is how we would calculate Taylor series. Some famous ones. And these ones you should just know. E to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, dot, dot. E to the ix turns out to be cosine x plus I, bless you, sine of x, where I is the square root of -1. So cosine x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. Sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on and so on. The natural log of 1 minus x is negative x plus x squared over 2 plus x cubed over 3 plus dot, 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 while the log of 1 plus x is x minus x squared over 2 plus x cubed over 3 x dot, dot. So these are some of the more famous Taylor series expansions. These are extremely valuable to know. And the fact that e to the x is cosine x plus I sine of x gives you some idea of where the trig identities come from. The trig identities come from complex analysis. They come from the exponential function. And you can even write cosine x as e to the ix plus e to the minus ix over 2, and sine of x as e to the ix minus e to the minus ix over 2i. Anybody remember the notation? Cis x or cis theta, CIS theta from high school, cosine plus I sine. Okay, my daughter saw this in her algebra 2 stuff recently, and I was just wondering who still uses this notation. When you did tangent inverse, did you do arctan or did you do tan to the -1? I actually prefer arctan, so that it's clear that it's the inverse is not 1 over, because we do have the 1 over for the trig functions with the cotangent and whatnot. So it's just worth knowing what notations people use. Okay, so these are extremely famous. So imagine I give you f of x is cosine x cubed plus 2x. What would f of 0 be? It would just be 1. What would f prime of x be? Do you know what cosine is? So it would be negative sine x cubed plus 2x. And then we have to take the derivative of x cubed plus 2x, which is 3x squared plus 2. So what's f prime of 0? F prime of 0 is not negative sine of 2. It's just 0, because we have a sine of 0. All right, so that's not so bad. All right, f double prime of x. I could do it. I have no desire to do it. Right? But we would just take the derivative, and then we would evaluate it at 0. So if I wanted to find the Taylor series of the cosine of x cubed plus 2x, I could do it without any trouble. How would I take the derivative of f prime of x? Yes. That's one way to do it. How else could I do it? Yes. Okay, there's another one. How would I do it if I had to do it? Mathematica, right? And in a strange coincidence, I seem to have a mathematical window already open on my computer for today's lecture. Yeah. Would one, yeah, exactly. So let's define f of x sine of x plus 2x. Derivative of f of x with respect to x. Derivative of the derivative. And if you look at that, you can now see, oh, okay, the second derivative is not going to be 0 at 0. The sine piece is still going to vanish. But the cosine piece is going to give us a -2. So start share, back. So if I do all this will give me f double prime of 0 is equal to -2. So the Taylor series of f of degree 2 would be f of 0 plus f prime of 0x plus f double prime of 0 over 2x squared. And that would just be equal to 0 plus 0, so it'd just be -x squared. So that would be the Taylor series of my function. Let me show you the faster way to do this. So we have f of x is cosine x cubed plus 2x. We know the cosine of u is 1 minus u squared over 2 factorial plus u to the 4th over 4 factorial minus ... What should we take for u? Yeah, x to the 3rd plus 2x. If you want, you could even view it as x times x squared plus 2. So then the cosine of x cubed plus 2x. Oh, so sorry, on the last page, I said it was 0. It's actually 1 minus, because f of 0 is 1. So just 1 minus x squared. I don't care enough to go back in time and slice the video. All right, so cosine of x cubed plus 2x, I just replace u in the expansion for cosine with x cubed plus 2x. So it's just going to be 1 minus x cubed plus 2x squared over 2 factorial plus x cubed plus 2x 4 factorial plus 2. Hope you didn't make any mistakes. Oh, I did. Okay. It's -2 plus 3x squared. I didn't say there was a square. Right. If you look at the, this is why I need glasses. There's a 2 over here by the 2 plus 3x squared. What is f double prime of 0? It's not 2, it's what? What's f double prime of 0? -4, not -2. So this should be -4 over 2, so it should be 2x squared. Okay. So when I go over here, if I want the second order Taylor series expansion, can the x cubed plus 2x to the 4th term, can that give me any second order pieces? Can it give me any piece of degree 0, 1, and 2? When I look at x cubed plus 2x to the 4th, when I expand that out, what's the smallest degree when I expand out things from x cubed plus 2x to the 4th? So x cubed plus 2x to the fourth. This is just going to be x to the fourth times 2 plus x squared to the fourth. This is x to the fourth, 2 to the fourth, plus 4 times 2 cubed x squared plus 6 times 2 squared x to the fourth plus 4 times 2 times x to the sixth plus x to the eighth. I'm just using the binomial theorem of Pascal's triangle. So if I expand x cubed plus 2x to the fourth, I have terms of degree x to the fourth, x to the fifth. I'm sorry, I have terms of x to the fourth, x to the sixth, x to the eighth, x to the 10th, x to the 12th. Can this contribute a 0th order term? No, nor first order, nor second order, nor third order. If I look at x cubed plus 2x squared, this is x squared times 2 plus x squared squared. So this is going to be x squared times 4 plus 2 times 2 times x squared plus x to the 4th. So this is going to be 4x squared plus 4x to the 4th plus x to the 4th. So the only term that this can contribute to a degree 2 Taylor series expansion is the 4x squared. So if I wanted to calculate the third order Taylor series, there would be no difference between the third order and the second order. If I wanted to calculate the fourth order Taylor series, for the fourth order, which pieces would contribute for the fourth order? Yes. Yes, it would be x to the 6th. Sorry. So the second order Taylor is going to just be 1 minus 4x squared over 2 factorial is 1 minus 2x squared as before. And you see, I hope, how much easier this is to compute than what we did before. Rather than taking all these derivatives, once we've taken the derivative of cosine, we've taken the derivative of cosine. This is just taking advantage of the fact that we know the Taylor series of cosine to now handle the Taylor series expansion of cosine of a more involved quantity. So if I wanted to do a fourth order Taylor series, for fourth order, which terms in the x cubed plus 2x squared would contribute up to fourth order? So which terms would be fourth order or less? So the order is the degree of x. So when you look at x cubed plus 2x squared, which terms here of degrees 0, 1, 2, 3, or 4? So can somebody read out the expansion for x cubed plus 2x squared? What is x cubed plus 2x squared equal? So if you can't answer this, this means you do not know what we're talking about, and you should be raising your hand and saying, I don't understand what we discussed. So can somebody tell me where is the expansion on this page for x cubed plus 2x squared? What does that equal? Good, 4x squared plus 4x to the 4th plus x to the 6th. So the degree of the term is just the exponent. So what's the degree of x squared? 2. What's the degree of x to the 6th? 6. So somebody else, which terms in 4x squared plus 4x to the 4th plus x to the 6th have degree at most 4? So somebody else, which term? Yes. The first two, the 4x squared and the 4x to the 4th. Those terms would contribute to a fourth order Taylor series expansion. Let's look at x cubed plus 2x to the fourth. We're going to which terms over here would contribute to an x to the fourth or less. Just the first one, just this piece over here. The next one is going to be an x to the sixth. So if I wanted to calculate the fourth order Taylor series, now the x cubed plus 2x to the fourth over 4 factorial, that would begin to contribute. It would give us a 2 to the fourth x to the fourth over 4 factorial. And then everything else would be degree 6 or higher, wouldn't matter. And if I looked at the next term, x cubed plus 2x to the sixth over 6 factorial, everything there is going to be at least an x to the sixth, so it's not going to matter. So the fourth order is just going to be 1 minus 2x squared. And now I'm going to have a plus 4x to the fourth from this, plus a 16x to the fourth, 4 factorial. And so that would be the fourth order Taylor series expansion. So is everybody comfortable with how you can calculate these Taylor series much faster if you happen to know the constituent, the building block, the starting point? So if I know cosine, I expand cosine and I just say, okay, well, what is the argument? If I now want something in terms of x and y, let's say I give you now, let's say f of x comma y is cosine of x plus y. So I now have something of two variables. There are a couple of ways to do this. Some ways are better than others. I could start by saying, I know the cosine of u is 1 minus u squared over 2 factorial plus u to the fourth over 4 factorial minus dot dot dot. So what would I want u to be? X plus y. And then the degree of, say, x to the a, y to the b is a plus b. So if I want a Taylor series of degree 5, I want all combinations of x and y of degree at most 5. And so I would get cosine of x plus y is 1 minus x plus y squared over 2 factorial plus x plus y to the fourth over 4 factorial. So second order Taylor is 1 minus x plus y squared over 2 factorial is 1 minus x squared over 2 minus xy minus y squared over 2, if you want to multiply it out. So this is one way that I can calculate the second order Taylor series. And if you think about it, for the Taylor series in one variable, we wanted all the derivatives up to the degree of the Taylor series to equal all the derivatives of the original function at the origin. And so we're going to want something similar to be true when we have a function of several variables. Who wants to see a really bad way to do this problem? Here's a bad way. Well, f of xy is cosine x plus y is cosine x cosine y minus sine x sine y. And so this is then 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus dot dot times 1 minus y squared over 2 factorial plus y to the fourth over 4 factorial minus dot dot minus, and then sine repeats, x minus x squared cubed over 3 factorial plus x to the fifth over 5 factorial minus dot dot y minus y cubed 3 factorial plus y to the fifth over 5 factorial minus. I could say, hey, let's use the trig identities. If I use the trig identities, I now just have to multiply everything out. And if I start to multiply everything out, I only want to keep degree 2, when I look at the first two products, the first product, when I multiply, how can I multiply something in the first by something in the second and have something of degree at most 2? I could have 1 times 1, which is 1. Could I have 1 times negative y squared over 2? Yes. And I could have negative x squared over 2 times 1. But I can't have x to the 4th and the y to the 4th coming in at all. So from the first two, I would just get 1 minus x squared over 2 factorial minus y squared over 2 factorial plus terms of degree 3 or more. Now what about the next product? Which terms, when I multiply, will give me something of degree 2 or less? Yes, just x times y. So we get minus x times y plus terms of degree plus terms of degree 3. And so I just wanted the second order Taylor. I would get the same thing. It's a little bit more work. And as you want to get more and more terms, it becomes harder and harder and harder. All right, so these are cheap shortcuts to calculate Taylor series expansions of functions of several variables. If you can reduce it to a nice function whose expansion you already know, and just shove in the new quantity, then you're golden. But more generally, let's say we have f of x, y. We'll just do something with 2 variables. Can you imagine doing 3 variables? Or you just keep adding more things. It should be f of 0, 0. Right? And then it should be df dx at 0, 0 times x plus df dy at 0, 0 times y. And if I now take the derivative with respect to x or with respect to y and set everything equal to 0, I would get just df dx at 0, 0, df dy at 0, 0. Now I have to start looking at terms of degree 2. So how can I get an x squared? I would have to have 2 derivatives with respect to x. So I could have a d squared f dx squared at 0, 0. And an x squared over 2, or actually 2 factorial. I could have a d squared f dy squared at 0, 0 times y squared over 2 factorial. And what's the remaining thing I could have? What else could I have? What's the only other way to get a derivative of what it's? I could take derivative with respect to x twice, derivative with respect to y twice, do each one once. And so I could have d squared f dx dy and d squared f dy dx. But if my function is nice, what do I know about those 2 derivatives? They should be the same. So for nice functions, it should be d squared f dx dy xy. And notice I don't have to divide by 2 factorial, because if I take dx dy, d by dx by dy, the d by dx hits the x and gives me 1. The d by dy hits the y and gives me 1. And so then when I put in 0, 0, it's just evaluated 0, 0 times xy. So note derivatives up to and including second order match derivatives of f at 0, 0. So now if I want to continue going, I would have to put in all the combinations for degree 3. All right. So let's try to look at what's going on. So let's look at it piece by piece. Let's start off with this piece. This looks similar to anything we've seen before. It's been a while. It's been an integration for so long. What's df dx df dy? What does that remind you of? So this is corresponding in one dimension to the f prime of x times x. So this is df dx at 0, 0, comma, df dy at 0, 0, dotted with xy. This is the gradient of f at 0, 0, dotted with xy. Basically, the expression. And so we could actually write this in vector notation or matrix notation as df dx at 0, 0, df dy at 0, 0, and then x and y. And this is the generalization of the f prime times x. Who here is potentially a physics major? As if you're potentially a physics major, you have this wonderful thing called quantization. You take something that's classical, you say, well, we're no longer going to allow things to be continuous, we're going to have things discretized. What happens as we go down to the quantum? And the classical world is basically the limit as h bar goes to 0. But the fact that h bar is a small positive number causes no end of parting. And so the question is, how do you quantize classical objects? Well, if I give you, f prime times x, the natural analog of this is just the grad of f dotted with xy. And so this explains where that term comes from. All right, let's now look at the next term. The next term is a little bit more involved. So we have something like this. And this is supposed to correspond to f double prime of 0 x squared over 2 vector. On the last page, this shouldn't be f prime of x, this should be f prime of 0. So we want to generalize f double prime of 0 over 2 factorial times x squared. It's really hard, to have vectors on vectors. I can do a dot product, but I've got to do an x squared and still multiply by f double prime. Well, there actually is a nice way to do this. d squared f dx squared at 0, 0, d squared f dy squared at 0, 0. I always forget which way it goes. I may be off, I may have my matrix flipped, I don't know. D squared f dx dy at 0, 0, d squared f dy dx at 0, 0. I may have flipped which one is the dx dy and which one is the dy dx. I don't know. And now, amazingly, if I put in a factor of 1/2, I put in the vector xy here, and I put in the vector xy here, this will equal this. This is the generalization of the f double prime 1/2 f double prime of 0 x squared. Is I take my x and have it once as a vector that is a column, once as a vector that's a row, and I have a matrix. And so this is called the Hessian. And usually, d squared f dx dy will be d squared f dy dx. So it will be real symmetric. And what it means for matrix to be symmetric is the stuff above the diagonal is the same as the stuff reflected below the diagonal. turns out a lot is known about these matrices. They have tremendously wonderful properties. Now, if we wanted to go further, we would have to figure out how do you write the f triple prime of 0 over 3 factorial times x cubed. And this is where tensors come into play. For those of you who are matrix, just listen to that. Okay. I'm done. Okay. This is more than enough, I think, to give you a sense of what's going on. And this is when we start to say, screw this, I'm going to just start to look at things forward. It's a little bit of a disappointment to look at things forward. It's nice to be able to look at things and build intuition, but it gets harder and harder and harder the more things you have. And so you start to look at maybe my expansion is maybe the Taylor series of f at, I guess I'll just do it in 2 dimensions, would be maybe so like a sum, n goes from 0 to infinity, a sum k goes from 0 to n, and then I would want dnf, and then I would have d x k dy to the n minus k at 0, 0, x to the k y to the n minus k divided by k factorial n minus k factorial. So something like that should work. And now if I take k derivatives of my initial function with respect to x, and n minus k derivatives of my function with respect to y, and set everything equal to 0, the x to the k will give me a k factorial times that. The y to the n minus k will give me n minus k factorial to the n minus k factorial, and this at 0, 0 will just be that. So what I'm doing is I'm saying, look, I'm going to expand it, and each one of these is going to be all the terms of degree n. So I'm going to collect all the times I do exactly n derivatives. And if I want to have exactly n derivatives, if I take k derivatives with respect to x, I've got to take n minus k derivatives with respect to y. If you look at this, it's really close to right. I could, of course, have 3 variables, x, y, and z, in which case I would have maybe k derivatives with respect to x, L derivatives with respect to y, and then n minus k minus L derivatives with respect to z. The notation just becomes worse and worse and worse. And this is why we start to invent powerful notation. But essentially, this is what's going on. And I'm just, keeping all the derivatives to a given degree. And I'm calling that, this would be the nth order term in my Taylor expansion. If I want a Taylor series expansion of degree of degree 2, I would just take k goes from 0. I would just take n goes from 0 to 2. I would not include the other stuff. And again, we didn't want to be able to prove, does something like this converge? And if it converges, does it converge to the original function? So if I give you a function, you can now use these formulas and just start calculating the derivatives. It's nice to interpret the first derivative as the gradient of f at 0, 0 dotted with x, y. This is your direction derivative. All right, well, this makes sense. When I'm looking at my Taylor series, I start at f of 0, 0. And in a small amount of time, I look at my gradient and look at how much am I changing if I move in the direction x, y. Then if I want to do a little bit better, the Hessian is starting to give me my matrix of acceleration in some sense. There is a dispute in the community as to what is the correct order to do math in college. There's no dispute that you should do math. You have to give. It's what order should you do math? What should you take after calculus 1? Calculus, that seems pretty logical, right? What should you do after calculus 2? Calculus 3 is a natural extension. There really is no calculus 4. Maybe vector analysis. So calculus 3 is a natural candidate to follow calculus 2. What else might be a natural candidate? Even though it's mathematics, sports. Yes, that is going to be a fun one. And if you had been wearing your hat, I was going to wear this one, but since you're not, it would be kind. Linear algebra. So this is the great divide. And so I was visiting my niece this weekend in Boston, and she's a few years younger than my daughter, and they had an autistic challenge, and they were asking you whose one is better. And of course, as adults, you hate to say which kid is doing a better job than the other. And so we tried as many different linguistic gymnastics to get out of saying this one is better than this one. I really like this feature you had over here. I really like this lighthouse. That was a water bottle. Oh, okay, water bottle. I really like the water bottle. Instead of arguing between linear algebra and multivariable calculus, what could you do? Both. So there are some schools that actually have a year-long class on linear algebra and multivariable calculus. And what you do is you do a little bit of linear algebra at the beginning of the year, and then you switch to multivariable calculus, and you switch back, and you keep going back and forth. So that when you get to certain points, you have the linear algebra language to understand what's going on. There are some theorems in multivariable calculus, which I think the best way to describe them is Moses came down from Mount Sinai and have these rules as to when you have a maximum and minimum. In one variable calculus, does anybody remember the second derivative test for maximum or minimum? Second derivative test? Yes. So if f prime of 0 equals 0 and f double prime of 0 is blank, have a max. And if f double prime of 0 is blank, have a min. So when do you have a max? So when it's negative. And when do you have a max? I'm sorry. You have a negative, you have a max, and if you have a minimum, it's positive. If you're ever not sure, take the functions x squared and negative x squared. And you go to 2x and 2, you go to negative 2x and negative 2. And so by just looking at x squared and negative x squared, you can rederive the second derivative test. I know that there is such a thing as a second derivative test, and I know it involves whether or not something is positive or negative, but I can't remember which way it goes. That's okay. As long as you remember the broad general outlines that such a test exists, just try it on a certain function. Because I can tell very easily, this is the level of my art, if I had to be competing, I can draw a parabola. I can do a better job if I really had to. I'm not trying to do my best parabola here. But if I had to draw x squared, I could draw it like this. And I can tell, oh, okay, with x squared, the second derivative is positive. This is a minimum. And with negative 2, it's a maximum. Okay, so that's more than enough for me to figure out what the second derivative test is. In several variables, if I want to find out if I have a maximum or minimum, step 1 is I want the gradient to be 0. So if I give you f of x, y, this is approximately f of 0, 0, plus the gradient of f at 0, 0, dotted with x, y, plus 1/2 x, y, the Hessian of f at 0, 0. That was our matrix, x, y, where the Hessian of f at 0, 0 was the second derivative of f at 0, 0, second derivative of x, y, and since it's symmetric, I can just write it the same way. And so there should be a second derivative test involving the Hessian. So I need to understand the second term to determine if I have a maximum or minimum. So depending on who's teaching linear algebra, you might actually get some results about this to help you figure out if you have a maximum or minimum. And of course, you could have a function that has more than just 2 variables, so things become harder and harder and harder. What is the easiest matrix to study? Easiest matrix. 2 by 2. Which 2 by 2 matrix? I had to give you a 2 by 2 matrix. Which 2 by 2 matrix would you want? One with all zeros. Well, if it's all zeros, well, remember, the second derivative test gives you no information if it's all zeros. So while the matrix of all zeros is easy to study, I'm not going to let you do that because it's not going to help. So what's the next easiest type of class of matrix that might be easy to study? Can anybody give me a type of matrix that would be easy to study? Okay, all ones, something easier than all ones. So it's diagonal matrices. So has everybody seen how to do matrix multiplication? So if I have x, y, a, b, c, d, x, y, this is x, y, and then a, b, c, d on x, y becomes ax plus by for the first one. Now I take low dotted with color, and then bottom would be cx plus dy. So then I would get ax squared plus by squared plus cx squared plus dy squared. It's I get ax squared, it's going to be plus bxy. And then the next one will become cx squared plus dxy. So it's going to be, no, let's put it dy squared. So it's going to be, no, it's c. So it's going to be x times ax plus by, and it's going to be y times cx plus dy. So it's going to be cxy plus dy squared. There we go. So it's going to be ax squared plus b plus c xy plus dy squared. So if b plus c is 0, this is going to be very easy to analyze. But for our matrices are symmetric. So for us, b equals c. If b equals c equals 0, it's easy. So if I give you xy, a0, 0, d, xy, this is just ax squared plus dy squared. So if a and d are greater than 0, then ax squared plus dy squared is greater than 0 as long as xy is not 0, 0. So if a and d are both greater than 0, then ax squared plus dy squared is greater than 0. So that means as long as I'm not at 0, 0, my Taylor series approximation is going to be a little bit larger than f of 0, 0. So I have a maximum minimum. So it's always going to be a little bit larger if I wait 0, 0. So it's going to be a minimum. If a and d are both less than 0, then ax squared plus dy squared is less than 0 as long as xy is not 0, 0. So what do we have? If one of AD is positive and one is negative, it's not. It would be a minimum in one direction and a maximum. So what we see is we can actually understand the behavior in the special case when dx dy, so d squared f dx dy is 0. So we'll just end with the following. Remember how we know how to find the equation of an ellipse that's oriented like this? If I give you an ellipse oriented like this, the solution is what you do is you change your coordinate axes to be like this, and then we can analyze it. So I might say a few more words. but that's what you do to determine if you have a maximum or minimum. We change our coordinate system so that the matrix of second derivatives is diagonal. And that's where linear algebra comes in. So linear algebra just allows us to change to a situation like that. And that's one of the big applications you should see in linear algebra. All right, so this is a good place to stop. Enjoy the weather. It looks like a glorious day.